Hello, how's everyone doing? I'm going to be learning C++ again. I've switched off live chat. I think when I will get a second monitor, then I'll put live chat back on because I'm streaming with one monitor only. Let me just change to full screen. Yeah, so last video, I did arrays and loops. So I was studying about arrays and STD vector. And I think I did this FISBUS question. I did this question. And yeah, so I'm basically going to be starting the next chapter, arrays, loops, and sign challenge solutions. In lesson 4.5, we noted how we generally prefer to use signed values to hold quantities because unsigned values can act in surprising ways. However, in lesson 16.3, we discussed how STD vector uses unsigned integral types. Unsigned integral type STD size t for length and indices. This can lead to problems such as this one. So print reverse. Okay, so we have an array over here. They're doing print reverse. And then they're starting with size t, std size t, index. Okay. So they have index of type of the size type of whatever type the size has. They're doing array dot size -1, which is the length of the array. And as long as the index is more than 0, they will keep looping. And in each loop, they will subtract index by 1. And then they're outputting this. So, like to me, I don't see a problem so far. These codes begin by printing the array in reverse. Okay. And then exhibits undefined behavior. It might print garbage values or crash the application. There are two problems here. First, our loops execute as long as index is more than or equal to 0. In other words, as long as index is positive, which is always true when index is unsigned. Therefore, the loop never terminates. Hold on. So if it reaches 0, and then you do minus minus, it will go to the largest value, right? Let's just remove all this. And so int a is 0. Let's do unsigned. Unsigned int is 0. So std a and then a minus 1. Second, when we decrement index, when it has value 0, it will wrap around to a large positive value, which we will then use to index the array on the next iteration. This is an out-of-bound index which will cause undefined behavior. Does std vector allow you to index out of the array? I have the chat switched off, so no point in asking. But like in comments, someone can answer. And while there are plenty of ways to work around these specific issues, these kinds of issues are magnets for bugs. So a is 0, then a minus 1 is this large integer. Now, if we do std vector v 1, 2, 3, 4, can I do v 10? Let me remove this. A is unused. Okay, so it does allow out of bound index. I thought vector like checks for out of bounds. Using a signed type for a loop variable more easily avoids such problems, but has its own challenges. Here's a version of the above problem that uses a signed index. So yeah, index st. So we are turning it into an integer, and then we are doing the same thing. Why do we need to convert it to size t? So if I have an integer a is equal to 2, I can put a here, right? Why does the index have to be unsigned? Argument conversion from int to const int unsigned mismatch. So the compiler doesn't allow it. So array static cast size t index is particularly hard to read. In this case, we have improved safety at a significant cost to readability. Here's another example using signed index. So we have length. Okay. T average. Oh, they're calculating the average. Okay, the cluttering of our code with static cast is pretty terrible. So what should we do? This is an area where there's no ideal solution. There are many viable options here, but we will prefer to in order to from what we believe is worst to best. You will encounter all of these in codes written by others. If you're wondering why signed unsigned conversions warning are often disabled by default, this topic is one of the key reasons. Every time we subscript a standard library container using a signed index, a signed conversion warning will be generated. This will quickly fill up your compilation log. Uh, so one way to avoid having to deal with lots of signed unsigned conversion warnings is to simply leave those warnings turned off. This is the simplest solution, but not one we recommend. Many developers believe that since the standard library array types were designed to use unsigned indices, then we should use unsigned indices. This is a completely reasonable position. We just need to be extra careful that we do not run into signed unsigned mismatches when doing so. If possible, avoid using index loop variable for anything but indexing. In lesson 16.3, we noted that the standard library container classes define nested def type, size type, which is an unsigned integral type used for array lengths and indices. The size member function returns size type. An operator uses size type as an index. So using size type as a type of your index is technically most consistent and safe unsigned type to use. So they have an array over here, vector. We have an integer vector size type. However, using size type has a major downside because it is a nested type. To use it, we have to explicitly prefix the name with the fully templated name of the container. This requires a lot of typing, is hard to read, and varies depending on the container and element type. When used inside a function template, we can use t for the template argument. Type name keyword prefix required for dependent type. Any name that depends on a type containing a template parameter is called a dependent name. Dependent names must be prefixed by the keyword type name in order to be used as a type. You may occasionally see the array type alias to make the loop easier to read. A more generous solution is to have the compiler fetch the type of the array type object for us so that we don't have to explicitly specify the container type or template arguments. To do so, we can use the declare type keyword which returns the type of its parameters. If array is a reference type, then above doesn't work. We need to first remove the reference from array. Okay, so the declare type will resolve to the type of the array. Because size type is almost always type def for size t, many programmers just skip using size type altogether and use the easier to remember type std size t directly. Unless you're using custom allocators. Although it makes working with standard library container types a bit more difficult, using a signed loop variable is consistent with best practices employed in the rest of our code. And the more we can consistently apply a best practice, the fewer errors we will have overall. There are 3, sometimes 4 good options here. Unless you're working with a very large array, using int should be fine. Okay. If you're dealing with very large arrays, or if you want to be a bit more defensive, you can use the strangely named std printf t. This type def is often used as the signed counterpart to size t. Why is the name like? What does this name mean? Because printf has a weird name, another good approach is to define your own type aliases for indices. You'll show a full example of this in the next section. Defining your own type alias also has a potential future benefit. If the C++ library ever releases a type designed to use as a signed index, it will be easy to either modify index to alias that type or to replace or find index with whatever type is named. In cases where you can derive the type of your loop variable from the initializer, you can use the auto to have the compiler deduce the type. In C++23, the z suffix can be used to define a literal of the type that is the signed counterpart to size t. Getting the length of an array as a signed value. Pre C++20, the best option is to static cast the return value of the size member function or std size to a signed type. That way, the unsigned value returned by array.size will be converted to a signed type, so our comparison operator will have two signed operands. Because signed indices won't overflow when they go negative, we don't have to wrap around. We don't have the wraparound problem we ran into when using unsigned indices. The unsigned value returned by array.size will be converted to a signed type. Okay. The downside of this approach is that it clutters up our loop, making it harder to read. We can address this by moving the length out of the loop. So auto length static cast array.size. In C++20, use size. If you want more evidence that the designer of C++ now believe that signed indices are the way to go, consider the introduction of size, signed size. This function returns the size of an array type as a signed type. We have index signed size array -1. But the thing is, we are doing static cast every time. Hold on. Conversion from int to unsigned. Isn't there like a better way to do this? So if we have our initial problem, if we have this, the wrapping around part is the main point, right? Like that's the main problem, right? Let me see. So array dot size index is more than one and minus minus it will wrap around. Hold on, there's a issue here. Index is unsigned. I need to remove this. If this is less than or equal to 1, and then at the end you do 0. The return type of this is unsigned long, right? What's the return type of size? So let's see. Yeah, this works. So if they have the wrapping around problem with the unsigned integers, they could just end it with the with 1, and then the last one could be like outside. Wouldn't that solve the problem? So size t is unsigned long, and then size over here. Okay, let's see. Once we have assigned loop variable, where did I read this? Yeah, std s size. Once we have assigned loop variable, we are going to run into implicit sign conversion warnings whenever we try to use that signed loop variable as an index. So we need some way to convert a signed loop variable to an unsigned where we intend to use it as an index. The obvious option is to static cast a signed loop variable into an unsigned index. We showed this in the prior example. Unfortunately, we do this. We need to do this everywhere we subscript the array. Using a conversion function with a short name, size t to, what is z over here? Use is the suffix for literal of type size t. So we have to use index, and we are converting it to size t, and this is much shorter. Use a custom view. In the prior lesson, we discussed how std string owns a string, whereas std view is a view into a string that exists elsewhere. One of the neat things about std string view is that how it can view different types of strings, but keeps a consistent interface for us to use. While we can't modify the standard library containers to accept a signed integral integer, we can create our own custom view class to view a standard library container class, and in doing so, we can define our own interface to work however we want. In the following example, we define a custom view class that can view any standard library container that supports indexing. Our interface will do two things: allow us to access elements using the subscript operator with a signed integral value, and get the length of the character as a signed integral value. This uses operator overloading. Let me see. Signed array view, and then they're defining the operator which returns, or they're defining their own operator which returns the index, I mean the value in the index. Okay. See. In lesson 16.3, we noted that instead of indexing the standard library container, we can call the data member function and index that instead. Since data returns the array type of as a C-style array, and C-style arrays allow indexing with both signed and unsigned values, this avoids signed conversion issues. The only sane choice: avoid indexing altogether. All of the options presented above have their own downsides, so it's hard to recommend one approach over the other. However, there is one choice that is far more sane than the others: avoid indexing with integral values altogether. C++ provides several other methods of traversing through arrays that do not use indices at all. And if we don't have indices, then we don't run into all of these signed unsigned conversion issues. Two common methods for array traversal without indices includes a range-based for loops and iterator. Okay, so range-based for loops. So Fibonacci size t length. Although for loops provide a convenient and flexible way to iterate through an array, they are easy to mess up and prone to off by one errors. Because traversing forward through an array is such a common thing to do, C++ supports another type of for loop called a range-based for loop. It's simpler, safer, and work with all common types of common array types. The range-based for statement has a syntax that looks like this. For each iteration, the value of the current array element will be assigned to the variable declared in element declaration, and that statement will execute. Because of the int num Fibonacci. So first num will be 0, and then in the next loop num will be 1, and then num will be 1 again, and then num will be 2, and so on. Because num is assigned the value of the array elements, this does not mean the array element is copied, which can be expensive for some types. In cases where the container being traversed has no elements, the body of the range-based for loop will simply not execute. Because element declaration should have the same type as the array elements, this is the ideal case in which to use the auto keyword and let the compiler deduce the type of the array elements for us. That way we don't have to randomly specify the type and there's no risk of accidentally mistyping. Here's the same example as above but using auto as the type of num. Another benefit to using auto is that if the element type of the array is ever updated, auto will automatically deduce the updated element type, ensuring they stay in sync. Wait, hold on. Auto doesn't deduce references. A possible unintended copy is being made. For each iteration for this loop, the next std string element from words array will be assigned, copied into the variable word. Copying a string is expensive, which is why we typically pass std string to functions by constant reference. You want to avoid making copies of things that are expensive copy unless we really need a copy. In this case, we are just printing the value of the copy and then the copy is destroyed. It would be better if we could avoid making a copy and just reference the actual array element. Fortunately, we can do this by making our element declaration a const reference. Wait, but earlier they said it doesn't make a copy. Avoid element copies using references. Because num is assigned the value of the array element, this does mean the array element is copied. Oh, I might have read it wrong. Okay, so we have const, oops, const auto reference. When to use auto reference versus const auto reference? Normally we would use auto for cheap to copy types, auto reference when we want to modify the element, and a const auto reference for expensive to copy types. But with range based for loops, many developers believe it is preferable to always use const auto reference because it is more future proof. In this example, we have std vector containing string view. Since string view is normally passed by value, using auto seems appropriate. But when considering what happens if words is later updated to an array of string instead, the range-based for loop will compile and execute just fine. The word will now be reduced to the type of string. And because we are using auto, our loop will silently make expensive copy to string elements. We just took a huge performance hit. There are a couple of reasonable ways to ensure this doesn't happen. Don't use type deduction in your range-based for loop. If we would explicitly if we had explicitly specified the element type as string view, then the array was later updated to then when the array was later updated to string, the string elements would implicitly convert to string view. Use const auto reference instead of auto when using type deduction in your range-based for loop. Range-based for loop and other standard container types. Range-based for loops work with a variety of array types, including non-decayed C-style arrays. We haven't covered any of these yet, so don't worry if you don't know what these are. Just remember that range-based for loops provide a flexible and generic way to iterate through more than just std vector. Getting the index of the current element. Range-based for loops do not provide a direct way to get the array index of the current element. This is because many of the structures that are range-based for loops can iterate over do not support indices. However, because range-based for loops always iterate in forward directions and don't skip elements, you can always declare your own counter. However, if you're going to do this, you should consider whether you're better off using a normal for loop instead of a range-based for loop. Range-based for loop in reverse. Range-based for loop only iterate in forward order. However, there are cases where we want to traverse an array in reverse order. Prior to C++20, range-based for loops could not be easily used for this purpose, and other solutions had been employed. However, as of C++20, you can use std view's reverse capability of the ranges library to create a reverse view of the elements that can be traversed. Okay. So how long does this take? Is this like O of n complexity? Define std vector with the following names: Alex, Betty, Caroline, Dave. Okay, let me just uh, how do I replace? we have this, and then okay, so we have these names is vector string names, and ask the user to enter a name. Use a range based for loop to see if the name the user entered is in the array. So name in names, uh, std string username, and then username stdcn username. If name username, then what do we print? Std cout name was found. Bool found is true, true, and then no, false actually, and then change found to true. Like I can't exactly because my phone is right in front of my keyboard. I can't properly see my keyboard. Uh, if not found, then std cout username was not found. I don't know if this is good. I don't know if this is the right way to do it. Let's see. Oh, I missed this. iStream. So cn iStream does not define this operator as a conversion of type acceptable to the predefined operator. Too many characters in constant. This is line 17. Oh, whoops. Okay, so they want an input. Let's say Alex. Alex was found. I'll just ask for input. Input name. Bob. Bob was not found. So use std string view. If I do this const auto reference, would this be the same as using string view performance wise? So username. And shouldn't matter if I initialize it, like do an empty initialization. Modify your solution to quiz 1. In this version, create a function template called isValue in array that takes two parameters, a vector and a value. So isValue in array. So boolean isValue in array std. Hold on. Should do this. Std vector string and then username, input name. I'll write input name. And you don't need to. I should have broken the loop when the name was found, but never mind. And there's no need for found. I'll just return true. Return true. Otherwise return false. And then input name. And what else? This has to be std string. Let's just do it string view instead. Now you're going to be using this here. If is user in array names and then username, then you print username was found. Else, I don't think we need curly brackets. Username was not found. Was not found. But I don't like this. How we are doing this. This expensive copy. Okay, let's just see if this works, and then std string view. Name. We don't need this. Let's see. What is this? Function can be made static. Okay, let's just see whether this works. Input name Alex. Alex was found. And then again, input name Bob. Bob was not found. Okay, so can I do a reference to vector string? Yes, I can. So Bob was not found. Can I also do constant? Alex was found. The function should return true. They said to create a function template. Yeah, so how are we gonna create it? Is it always a string? Is value in it? Okay, wait, I think template type name T. So we have type T. So whatever this type is should always also be this type over here, a reference to this type. And then same thing here also. T here. Does this work? So let's see what's the issue. So string, we have string. Cannot convert constant ty to string reference. I don't want to make expensive copies. Pass it the array of the names and the name the user entered. A function template that is using template argument deduction will not do conversion to match the template type parameters. You can either call the call either matches the template or it doesn't. A template function with an explicitly specified template type argument will convert arguments to match the parameter type. So let's see type name, const std vector. Wait, isn't this what I did? Const std vector template. I think this may be the issue. Why does it say this? It's on line 9. That's where the issue is. Const auto. I think it has to be like this. Maybe. Yeah, Alex was found. And can this be made static? Bob. Bob was not found. So we have D. Is specifying the type name, which is string view. Okay. Array indexing. One of the bigger documentation problems with arrays is that integer indices do not provide any information to the programmer about the meaning of the index. Consider an array holding 5 test scores. Okay, and then test score 2, who does this represent? Using unscoped enumerators for indexing. In lesson 16.3, we spent a lot of time discussing how the index has type size type, which is generally an alias for size t. Therefore, our indices either need to be of type size t or a type that converts to size t. Since unscoped enumerators will implicitly convert to a size t, this means we can use unscoped enumerations as array indices to help document the meaning of the index. So yeah, Kenny 0, Kyle 1, and then we can do students star. In this way, it's much clearer that what each of the array elements represent. Using a non-constant expression, unscoped enumeration for indexing. The underlying type of an unscoped enumeration is implementation defined. Because enumerators are implicitly constant expression, as long as we stick to indexing with unscoped enumerators, we won't run into sign conversion issues. However, if we define non-constant expression variable of the enumeration type and then try to index our vector with that, we may get sign conversion warning on any platform that defaults unscoped enumeration to a sign type. So this is a non-constant expression. May trigger a sign conversion warning if student.names defaults to a signed underlined type. In this particular case, we could make name constant expression. However, that won't work when our initializer isn't a constant expression. An alternate option is to explicitly specify the underlying type of the enumeration to be an unsigned integer. In the above example, since name is now guaranteed to be an unsigned int, it can be converted to size t without sign conversion issues. Using a count enumerator, note that we have defined an extra enumerator at the end of the enumerator list named max student. If all the prior enumerators are using default values, which is recommended, this enumerator will have a default value matching the count of the preceding enumerators. Oh, so this has 5. And then we can use 5 over here. We use max students in two places. First, we create vector with the length of max students. So over here, and then they are also using an cout. Asserting on array length with a count enumerator. More often, we are creating an array using an initializer list of values with the intent of indexing the array with enumerators. In such cases, it can be useful to assert that the size of the container equals our count enumerator. If this assert triggers, then either our enumerator list is incorrect somehow or we have provided the wrong number of initializers. This can easily happen when a new enumerator is added to the enumeration, but a new initialization value is not added to the array. For example, you have these students, using the test scores. Ensure the number of test scores is the same as the number of students. So assert this. Arrays and enum class. Because unscoped enumerations pollute the namespace they are defined in with their enumerators, it is preferable to use enum classes in cases where the enum is not already contained in another scope region. However, because enum classes don't have an implicit conversion to integer types, we run into problem when we try to use their enumerators as array indices. So compile error, no conversion from student names to std size t. So then what is the type of this? Is it assigned integer? We can use static cast. Better option is to use a helper function that we introduced in lesson 13.6. So constant expression auto operator plus student name A. What is no except? I can't remember this. Return static cast std underlying type t student name. Create a program-defined enum inside a namespace containing the names of the following animals. Wait, hold on. So this is unscoped. They're saying it has to be in a namespace, right? So name space animals is the convention to use capital for namespace. Student names. So it's a Pascal case, right? Chicken, dog, cat, elephant, duck, snake. Enum. Wait. Okay, I will write type. Enum a type, animal type. For enum, is the convention to use capital letters. Hold on. So S is capital, N is capital. We have chicken, dog, cat. Chicken, dog, cat, elephant. Chicken, dog, cat, elephant. Duck, snake. And then we can have max animal. animal types. Define an array with an element for each of these animals and use an initializer list to initialize each element to hold the number of legs that animal has. Assert that the array has the correct number of initializers. Hold on. A program defined enum containing the names of the following animals. Define an array with an element for each of these animals. Okay, so I guess they're asking std vector number of legs like that. So 2, 4, 4, 4, 2, 0. And then we assert. How did they do the assert before? Assert std size std size num legs is equal to a animals max animal type. Is it like this? Write the main function that prints the number of legs an elephant has. Std cout you know, actually, yeah, elephant has legs. Number of legs animals elephant. Assert identify not found. C assert. Elephant has 4 legs. Let's see if that's what they did. Animals. Oh, they defined it over here. Const animals. Okay, STD vector resizing. So, in the remaining lessons of this chapter, we are going to focus on one thing that makes vector significantly different from most other array types: the ability to resize itself after it has been instantiated. Most array types have a significant limitation. The length of the array must be known at the point of instantiation and then cannot be changed. Such arrays are called fixed size arrays. Both array and C-style arrays are fixed size array types. We'll discuss these further next chapter. On the other hand, STD vector is a dynamic array. A dynamic array is an array whose size can be changed after instantiation. This ability to be resized is what makes a vector special. So resizing at runtime, step 3, the length is v dot size, the length is 3, so resize it to 5, now the length is 5. There are two things to note here. First, when we resize the vector, the existing element values were preserved. Second, the new elements are value initialized, which perform default initialization for class type and zero initialization for other types. Thus, the two new elements of type int were zero initialized to value 0. The length versus capacity of STD vector. Consider a row of 12 houses. We would say that the count of those houses is 12. If we wanted to know which of those houses were currently being occupied, we would have to determine that in some other way. When we only have a length, we only know how many things exist. Now consider a carton of eggs that currently has 5 eggs in it. We would say that the count of eggs is 5, but in this context, there's another dimension we care about: how many eggs the cartons could hold if it were full. We would say the capacity of the carton of eggs is 12. STD vector also has a capacity. In the context of vector capacity is how many elements the vector has allocated storage for, and the length is how many elements are currently being used. A vector with a capacity of 5 has allocated space for 5 elements. If the vector contains 2 elements in active use, the length of the vector is 2. The 3 remaining have memory allocated for them, but they are not considered to be in active use. We can ask vector for its capacity via the capacity member function. Wait. So we have capacity. So size is how much is being used. In this case 3. Then capacity is how much it holds, how much it can hold. But the length is the same. The length and capacity are like, doesn't size and capacity give the same number? What's the case where they are different? When vector changes the amount of storage it is managing, this process is called reallocation. Informally, the reallocation process goes something like this. The vector acquires new memory with capacity for the desired number of elements. These elements are value initialized. The elements in the old memory are copied into the new memory. The old memory is then returned to the system. Capacity and length are set to the new values. From the outside, it looks like the vector has been resized, but internally, the memory has actually been replaced. Because reallocation typically requires every element in the array to be copied, reallocation is an expensive process. As a result, we want to avoid reallocation as much as reasonable. Why differentiate length and capacity? A vector will reallocate its storage if needed. Uh, if a vector only kept track of its length, then every resize request would result in an expensive reallocation to the new length. Separating length and capacity gives vector the ability to be smarter about when reallocations are needed. The following example illustrates this. So create a length vector with length 5. So print capacity and length. Okay. So 5 and 5. And then they're printing each value over here 0, 1, 2, 3, 4. Resize vector to 3 elements. So resize it to 3. We could assign a list of 3 elements here. Print capacity and length. Capacity is 5, length is 3. Now resize vector back to 5 elements. Capacity is 5, length is 5. When we initialized our vector with 5 elements, the capacity was set to 5, indicating that our vector initially allocated space for 5 elements. The length was also set to 5, indicating that all elements are in use. After we called v.resize 3, the length was changed to 3 to fulfill our request for a smaller array. However, note that the capacity is still 5, meaning that the vector did not do any reallocation. Finally, we call resize 5 because the vector already had a capacity of 5. It did not need to reallocate. It simply changed the length back to 5. And a value initialized the last 2 elements. By separating length and capacity, in this example, we avoided 2 reallocations that would otherwise occurred. In the next lesson, we will see example where adding elements to vector one by one. In such cases, the ability to not reallocate every time length changes is even more important. Vector indexing is based on length, not capacity. You may be surprised to find that the valid indices for the subscript operator and at member function is based on the vector's length, not the capacity. When v has a capacity 5 and length 3, only indices from 0 and 2 are valid, even though the element with indices between the length of 3 and capacity of 5 exist. Their indices are considered to be out of bounds. Resizing a vector to be larger will increase the vector's length and will increase its capacity if required. However, resizing an array to be smaller will only decrease its length and not its capacity. Reallocating a vector just to reclaim the memory from a small number of elements that are no longer needed is a poor choice. However, in the case where we have a vector with a large number of elements that we no longer need, the memory waste could be substantive. To help address this issue, std vector has a member function called shrink to fit that requests the vector shrink its capacity to match its length. So here's an example. Allocate room for 1000 elements. Okay. And then we are printing capacity and length, each of which is 1000. Resize to 0, capacity 1000, length 0, and then shrink to fit, capacity 0, length 0. And length is the number of elements currently in use, capacity the number of elements that have storage allocated. Capacity is tracked separately so that the vector can avoid some reallocations when the length is changed. Valid indices for a vector is based on length or capacity, it's based on length. std vector and stack behavior. Consider the case where you are writing a program where the user will enter a list of values In this case, the number of values that they will be entering is not known at compile time and could vary every time they run the program. You will be storing these values in a vector for display and or processing. Based on what we have discussed so far, there are a few ways in which you might approach this. First, you could ask the user how many entries they have, create a vector with that length, and then ask the user to enter that number of values. This isn't a bad approach, but it requires the user to know exactly how many entries they have ahead of time. Alternatively, we could just assume the user won't want to enter more than some number of values and create a vector with that many elements. Then we can ask the user to enter data until they are done or until they reach 30 entered values. The downside of this approach is that the user is limited to entering 30 values. We could address that problem by adding some logic to resize the vector larger whenever the user reaches the maximum number of values. But this means we are not now having to mix array size management with our program logic, and that is going to increase the complexity of our program significantly. The real problem here is that we are trying to guess how many elements the user may enter so we can manage the size of the vector appropriately. For situations where the number of elements to be entered is truly not known ahead of time, there is a better approach. Okay, so I already know about stack. The order in which items are added to or removed from a stack can be described as last in, first out. The last plate added onto the stack will be the first plate that is removed. In programming, a stack is a container data type where the insertion and removal of elements occur in a LIFO manner. This is commonly implemented via two operations named push and pop. So push, put new element on top of the stack, and pop, remove the top element from the stack. Many stack implementation optionally support other useful operations as well. Yeah, top or P, get the top element on the stack, but it does not remove. Empty, determine if the stack has no elements, and size, count how many elements are on the stack. Okay. In some languages, a stack is implemented as its own discrete container type. However, this can be quite limiting. Consider the case where we want to print all the values in a stack without modifying the stack. A pure stack interface does not provide a direct method to do this. In C++, stack-like operations were instead added to the existing standard library container classes that support efficient insertion and removal of elements at one end. This allows any of these containers to be used as stack in addition to their native capabilities. A stack or plate analogy is a good one, but we can make a better analogy that will help us understand. Instead of stack of plates, consider a column of mailboxes all stacked on top of each other. Each mailbox can only hold one item and all mailboxes start out empty. Each mailbox is linked to the mailbox below it. Okay, I guess I like the stack a plate one better. Stack behavior in std vector is implemented via the following member functions. So push back, put new element on top of the stack, xcali draw, so we have a stack. We push data in. So this is like 5, 6, 10, 2, 3, and then we pop out the data. So stack.pop. So if we do pop, we get 3. And then if we do pop again, we get 2. So we get 3, and then 3 goes out of the stack. Then pop again, we get 2. 2 goes out of the stack. Right, and for std vector, so this is in memory. This is the memory. So pushback, I think it adds to the end. So this is the entire length. This is the entire capacity and also the length. So pushback puts new element on top of the stack. So it actually adds element to the end of the vector. So pushback 5, and then if you do pushback 6, pushback 7, pushback 2, 1, 0, 10. So all of this is from pushback. And then pop back, remove the top element from the stack. So if we do pop, we pop 10 out, and then pop again, pop 0 out, and then back, top or peak, and then in place back. Alternate form of pushback that can be more efficient. Adds element to the end of the vector. Okay, I want to know the difference between pushback and in place back. So capacity and length, capacity 1, capacity 2, capacity 4, 1, 2, 3, and then pop back to 1, 0. Push back and in place back and increment the length of vector and will cause a reallocation to occur if the capacity is not sufficient to insert the value. The capacity jump from 2 to 4. Okay, they're referring to this. Even though we are only pushing one element, when pushing triggers reallocation, std vector will typically allocate some extra capacity to allow additional elements to be added without triggering another reallocation next time. And that is left up to compiler implementation. GCC and CRANG doubles the current capacity. Visual Studio multiplies the current capacity by 1.5. Reallocating a vector is computationally expensive. So we want to avoid reallocations when reasonable to do so. In the above example, we could avoid the vector being reallocated 3 times if we manually resize the vector to capacity 3 at the start of the program. So now if we do pushback, we get 1, 1, 2, and then 1, 2, 3. The issue here is that the parentheses initialization and the resize function set both the capacity and the length. Our vector is starting with a capacity of 3, but the length is also being set to 3. So our vector is starting with 3 elements having value 0. The elements we push on later are pushed on the top of these initial elements. The resize member function changing the length of the vector is fine when we are intending to do subscripts to access elements, but it causes problems when we are using the vector as a stack. What we really want is some way to change the capacity without changing the length. The reserve member function changes the capacity but not the length. The reserve member function can be used to reallocate a vector without changing the current length. Here's the same example as before, but we added call to reserve to set the capacity. So stack reserve reserve space for 6 elements, but do not change the length. So capacity 0 and 0. Capacity is now 6 and this 6. Length is 0. Oh, so now if we do pushback, it gets added to the at the start. Pushback and embrace back. Push an element onto the stack. If the object to be pushed already exists, pushback and embrace back are equivalent, and pushback should be preferred. In cases where we are creating a temporary object for the purpose of pushing it onto the vector, embrace back can be more efficient. So stack F A into pushback stack pushback F, and then stack and place back. When we need to create a temporary object to push, and place back is more efficient. So this creates a temporary object and then copies it into the vector, and emplace back forwards the argument so the object can be created directly in the vector, no copy made. Pushback won't use explicit constructors. Emplace back will. So this will cause a compile error, and this is fine. This makes emplace back more dangerous, as it is easy to accidentally invoke an explicit constructor to perform some conversion that doesn't make sense. Addressing our challenge using stack operations. It should now be obvious how we should address the challenge introduced at the top of the lesson if we don't know in advance how many elements will be added to our vector. Using the stack function to insert those elements is the way to go. So score list, handle bad input, std clear, std ignore, numeric limits, and then continue. Enter a score or -1 to finish. If you are done, break out of the loop. The user entered a valid element, so let's push it onto the vector. Okay, so ask the user for input, validate it. If it's -1, finish. Otherwise, push it to the score list. This program lets the user enter test scores, adding each score to the vector. After the user has finished adding scores, all the values in the vector are printed. Note how in this program we don't have to do any counting, indexing, or deal with array lengths at all. We can just focus on the logic of what we want the program to do, and let the vector handle all with the storage issues. Okay, next chapter. I think this is the last one. I think after this chapter, we'll just read the summary and end the stream. In lesson 0.1, we discuss how std bitset has the capability to compact 8 billion values into a byte. Those bits can then be modified via a member function of std bitset. Vector has an interesting trick up its sleeve. There is a special implementation for std vector boolean that may be more space efficient for billion values by similarly compacting 8 billion values into a byte. Unlike std bitset, which was designed for bit manipulation, vector bool lacks bit manipulation member functions. Using std vector boolean, for most part, vector boolean works like a normal vector. So on the author machines, this print this. Okay, so they changed the last one to 0. STD vector boolean has some trade-offs that users should be aware of. First of all, it has a higher amount of overhead because size of vector boolean is 40 bytes on the author's machine. So you won't save memory unless you're allocating more Boolean values than the overhead for your architecture. Second, the performance of vector bool is highly dependent upon the implementation. A highly optimized implementation can be significantly faster than alternatives. However, a poorly optimized implementation will be slower. Third and most importantly, std vector is not a vector, nor does it hold Boolean values, nor does it meet C++ definition of a container. Although a vector boolean behaves like a vector in most cases, it is not fully compatible with the rest of the standard library. Code that works with other element types may not work with std vector boolean. For example, the following code works when T is any type except boolean. Yeah, why won't boolean work here? Get reference to the first element. Is a reference to boolean not allowed? The modern consensus is that vector boolean should generally be avoided, as the performance gains are unlikely to be worth the incompatibility headaches due to it not being a proper container. Unfortunately, this optimizing version of vector boolean is enabled by default, and there is no way to disable it in favor of non-optimized version that is actually a container. There have been calls to deprecate vector boolean. The work is underway to determine what a replacement compact version vector of bool might look like. Our recommendation is as follows. Use constant expression bit set when the number of bits you need is known at compile time. Prefer a vector character when you need a resizable container of Boolean values. And space savings isn't a necessity. Favor a third-party implementation of dynamic bit set. Okay, so summary and quiz. I will just read the summary and then I will end the stream. So container is a data type that provides storage for a collection of unnamed objects. This number of elements in a container is often called its length. The term size is also commonly used for the number of elements in a container. In most programming languages, containers are homogeneous. The containers library is a part of C++ standard library. It contains the various class types that implement some common types of container. So this operator does not do any kind of bound checking. Arrays are one of the few container types that allow random access, meaning every element in the container can be accessed directly with equal speed. C++20 is size non-member function, which returns the length of as a large signed integral type, which is type normally used as a signed counterpart to size t. So at member function does a runtime bound checking. Move semantic refers to the rules that determine how the data from one object is moved to another. Okay. Write definition for the following. Use CTAD where possible. A vector initialized with the first six even numbers. Okay. Constant vector initialized with the values with these values. A constant vector of string view initialized with names Alex, Brad, Charles, and Dave. String view literals. Can't we use like angle brackets to tell the compiler that these are string views? A vector with a single element value of 12. A vector with 12 integer elements initialized to the default values. I will just read this and then I will end the stream. Let's say you're writing a game where the player could hold three types of items: health potions, torches, and arrow. Define an unscoped enum in the namespace to identify the different types of items. Define vector to store the number of each item type the player is carrying. The player should start with one health option, 5 torches, and 10 arrows. Assert to make sure that the array has the correct number of initializers. Define a count enumerator and use it inside the assert. The program should output the following. Let's just actually try this. So, item namespace items health potions health potion torches and arrows. Health potion torches arrows. Then std vector where the default value is 1, 5, and 10. Five and 10. Is this right? Count is 16 initially. Why is this causing an issue? Hold on. The player should start with one health option, 5 torches, and 10 arrows. I think it's this chapter. I want to know how to like initialize the value. I don't think we can do it in enum. Can we? Wouldn't using a struct be better here? I think enum by definition, it's like, it's not allowed. So health potions, torches, arrows and count. To store. Define std vector to store the number of each. Wouldn't a struct be a better data structure? Num items. So 1, 5, 10 arrows. Assert items. So size of items is max items. Define a count enumerator and use it inside the assert. The program should output the following. Player has items, num items. The player has 16 items. I guess we can loop through this for int num in items, number of items. In total is 0. Total plus equal num, then std cout player has items. Oops. Okay. Let's see. Count total items. Modify your program from the prior step so it now outputs. You have 1 health potion, you have 5 torches, 10 arrows, and 16 total items. So int count item std vector reference num items and index, I guess. Integer index, which is initially -1. If index is equal -1, then think you do it like this. Else, I think I should write it like this. Get item count. Return. I should write this here. Otherwise, return num item index. Player has these many items. Health potion. Torches. Arrows. Let's see what's the issue here. Use of class template requires template argument list. Sorry. What? So list of std vectors int. I think this is what they want. Conversion from int to constant unsigned. I can write unsigned over here. Nope, this is wrong. This shouldn't be unsigned. Hold on. Let's do this. Items, max items. This is the default. Otherwise, the user should be providing a number 0, 1, 2. And if it's 3, then assume that they want the total. One, 5, 10, and 16. So how did they do it? Get item name. Get item name single. Print inventory item. Scans std vector int reference and then item type. Hold on. Item type int. Type int. And then this will be I think it's better if it's unsigned int. If it was if the type is items type, items type, then this would work, right? But we have to convert it to unsigned. Or what if the type here was unsigned? Oh, it actually works. But shouldn't this be, is it unsigned by default? Hold on. Is there a way to std cout? How do I get the type of? I don't remember how you get the type. I'm assuming that this is unsigned type. Also, what happens if we do this? If I take this and let's say I put -1. Cannot convert argument 2 from int to item type. And if I, okay, so it can't. So if it's out of bound like this, so if I remember correctly, these are like distinct type, right? They're not integers. They're not called integers. Write a function that takes a vector and returns a pair containing the indices of elements with min and max values in the array. So vector 1, vector 2, the program should return minimum element has index 2 and value 2. The maximum element has index 1 and value 8. Now, what do they mean index 1? 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 5. But why is, oh yeah, this one actually. I guess it's using the first occurrence. So they're printing the array over here. Pair size t, size t. Uh, okay. Guess I will end the stream here then. There's some things I need to revise first before I start doing more questions. Okay, I will end the stream here and I will see you guys in the next stream. I think I will most likely do math, but depending on my mood, I will see. Okay, anyways, see you next time.